Okay, so we are going to start our lecture today. Students, please keep a track on the recording. If something happens, recording stops. If you notice that, just let me know, because when I'm focusing over the lecture, sometimes I do not really focus over if the recording is continuing or it hasn't stopped. Okay, so it will be your responsibility. Okay, so let's start with our lecture. Chapter number 4 we were discussing, and this chapter basically deals with the closed systems. Okay, so we have we were applying the first law of thermodynamics over the closed systems, and if you remember, we had uh, there is a formula sheet which I placed at the end, and we discussed approximately all the formulas within this formula sheet. Okay, so for example, if we have a constant volume process, volume is constant, that what will be the work done for it. If we have a constant pressure process, so PV power 0 equals to constant, means P equals to constant, so what will be the work done in this case. We talked about the polytropic process, which is the general case. PV power n is equals to constant. The work done in that case, we discussed about that as well in the last lecture. Then isothermal process is also is also a specific case of the polytropic process when n is equals to 1. So PV equals to constant. For this case, we have a bunch of formulas. These are basically one single formula, but different forms of those formulas. We discussed about that in the last class. So these were the 4 different types of work done. Okay, and then after that we also discussed about the amount of heat transfer. The amount of heat transfer in the constant volume process and constant pressure process. We discussed that for the constant volume process, it is Q equals to U2 minus U1. And for constant pressure process, it will be HQ is equals to H2 minus H1. So till here we discussed everything. Only this part of the problem, we said that this part of the formula we are going to discuss later. So, then after that, once we studied all these formulas, then we solved some of the problems. As I told you, there were 4 problems here. Out of the 4 problems, question number 2 I did with section A, and you guys said about question number 4, so I did question number 4 with you. And 1 and 3 is something you can cover it yourself. And the solution is here. You can go through it. As simple as that. Okay. Till this point here, anybody have any question, anything anybody do not understand, feel free to ask. Okay. So till here, everything is okay. Anybody have any query? Anybody have anything to ask? So I need your responses. Yes or no or whatever. You have any issues? Come on, man, no response. Are you able to understand the subject material till here, or do you think you have some issues in understanding? Any comment from anybody? No issues in understanding. Thank you. Anyone else have anything to say? It's important for me that you understand the subject material. If there is something that you don't understand, you have to communicate to me, okay? You have to let me know that this is something that you do not understand, so that I can really focus over it and help you understand that.
No, sir, we're understanding it quite well. Thank you.
Okay, good. Anyway, so let's start. Let's continue from where we stopped last time. Okay. So this problem, we have a gas in a piston cylinder assembly that undergoes an expansion process. for which the relationship between pressure and volume is given by PV power n is equals to constant. So since it is PV power n equals to constant, that means we are talking about polytropic process. The initial pressure is 3 bar, so this is P1, and the initial volume is 0.1 meter cube, so that will be V1. And the final volume is 0.2 meter cube, so that will be V2. Okay. Determine the work for the process in kilojoule. If n equals to 1.5, if n equals to 1, or if n equals to 0. So when n equals to 1.5, it is definitely a polytropic process. But when n equals to 1, what kind of process it is? Will it be a polytropic process? It will be a polytropic process, but it will be a special case of a polytropic process. And what is the name of that process if n equals to 1?
Sir, apologies, but are you sharing your screen because we can't see anything on the classroom?
Oh, okay. I'm not sharing the screen. Oh, okay, I got it. Thank you. Can you see the screen now?
Yes, sir.
Thank you for letting me know. You see, I forgot to share the screen. Okay, so let's just start back from here. So we have a gas in a piston cylinder assembly that undergoes an expansion process for which the relationship between pressure and volume is given by PV power n equals to constant. When we say PV power n equals to constant, this is a polytropic process. Okay. The initial pressure is 3 bar, means P1 is 3 bar. Initial volume is 0.1 meter cube, and the final volume is 0.2 meter cube. So we have P1, V1, and V2 given. Determine the work for the process in kilojoule if n equals to 1.5, if n equals to 1, if n equals to 0. When n equals to 1.5, this is definitely a polytropic process. So, but I was asking when n equals to 1, if I put n equals to 1, then what kind of a process it is? If you remember, we discussed a bunch of formulas before, and here we discussed that when n is equals to 1, this is a special process known as isothermal process. PV equals to constant. Remember that?
Yes, sir.
And when n equals to 0, this is a special process which is, it becomes P equals to constant, so constant pressure process. So when n equals to 0, that's a constant pressure process. When n equals to 1, this is an isothermal process. And if n is something else, then it might be a polytropic process. So we have a situation like this, that it is said that we have, in the question it is mentioned that we have a polytropic process, but we need to solve it for 3 cases: when n equals to 1.5, when n equals to 1, and when n equals to 0. We are given is P1, V1, and V2. Okay, so let's talk about the first case. First case is when n equals to 1.5. This will definitely be a polytropic process. So since it is a polytropic process, you'll say P1, V1 power n is equals to P2, V2 power n. We know n, and we know P1, and we know V1 and V2. So we can find what is P2. Okay. So once you have P1 and P2, then we can find what is the work done in this case. Okay. Because the work done for the case of a polytropic process is, let's go back into the formulas. The work done for the case of polytropic process is this: P2 V2 minus P1 V1 divided by 1 minus n. So you need P1, you need P2, you need V1, you need V2, and you need n. So we'll have all of these values with us. We just need to substitute them into the formula and solve it for this case. You can see here we have this P2 V2 minus P1 V1 by y upon 1 minus n. First thing is that we solve it for P2. What will be P2? Okay, and then after that substitute it into the main formula for the work done and get the work done for the case of a polytropic process. So this is the solution for part A. Okay, is this solution clear or not?
So can you go through the solution again, please?
Okay, I come to the solution. So we need to find out the work. Okay, but we are given in the question V1 and we are given in the question V2. We are given in the question P1 and we are given in the question N. But the P2 is not given. So first we find P2. And how do we find P2? Because we know that it's a polytropic process, so P1 V1N equals to P2 V2N. So here everything known except for P2, we'll find P2 and then we'll find the work done. Is it clear?
Yes, sir.
Okay. Part B and part C is not done here, but we can do it easily because it's the same logic. For part B, we have n equals to 1. So when n equals to 1, it's basically isothermal process. So when it is isothermal process, so we can do it here because we know, let's say we use this one. So this formula, because we know V2, we know V1, we know P1, and we know V1. So we have all the things known here for isothermal process. We can find out what is the work done for the case of isothermal process. Similarly, for the part C, it's a constant pressure process. So P V2 minus V1, we have V2, we have V1, we have P. So we just substitute all the values and get what is the work done for the constant pressure process. Anything within the solution of this problem which is not clear, please ask. Everything is clear so far? Are you catching up with me?
Yes, sir.
Okay, let's go to the next question. Okay, we have a frictionless piston cylinder device. Initially contains 200 liter of saturated liquid refrigerant R134A. So we have volume. This is the initial volume. Okay. The piston is free to move and its mass is such that it maintains a pressure of 800 kilopascal on the refrigerant. So when it says that it maintains a specific pressure, means pressure is constant. Maintains a specific pressure, means pressure is constant. The refrigerant is now heated until its temperature rises to 50 degrees. So that will be T2. When it maintain a pressure, pressure is given, so means we know what is P1 and we know what is P2 because P1 and P2 are same. Okay. Calculate the work done during this process. So we need to find what is the work done during this process. So first of all, what kind of a process it is? It's a constant pressure process because it maintains the pressure. For a constant pressure process, the formula for work done will be what? It will be P V2 minus V1. However, once you're going to solve this problem, once you go take the values of volume from the tables, you're going to get the specific volume. Specific volume is meter cube per kg. So you have to multiply it with the mass. Okay. So this will be the formula for work done for constant pressure. Okay. Now, first of all, what will be the approach of solving it? Okay, let's talk about mass. Pressure is given. Straight away pressure is given. We know what is P1 equals to P2. So this pressure is known. Okay, what about mass? Okay, what is said is that it is a frictionless piston cylinder device that initially contained 200 liter of saturated liquid. Saturated liquid means you know the quality of the liquid. What will be the quality of saturated liquid? X1 will be? What will be the quality of saturated liquid? X1 will be? It will be 0. Are you getting it up?
So why would it be 0?
Because it is saturated liquid. If it was saturated vapor, then X1 will be 1. If it was liquid vapor mixture, then X1 would be in between 0 and 1.
Okay.
Right? Okay. So we know that it is saturated liquid, and we know what is the pressure. So we have two parameters here, P1 and X1. We're going to use these two parameters to find out what is V1. Make sense? And what is V1? V1 is basically specific volume. Specific volume is volume per unit mass. The volume is given. This is the volume given. Specific volume you already determined. Then you will find what is the mass. Do you understand till this step or not, how we determine the mass? If it's not clear, I can explain you again, no problem.
No, sir.
So we have, it's clear? Okay. Okay, so we have the pressure and we know that it is saturated liquid. Whenever it is saturated liquid, what kind of values you're going to take? You're going to take the F values from the table. F values. Okay, so corresponding to the pressure, you're going to take the F value because it is saturated liquid, and then that will be VF. VF will be your specific volume, and then specific volume is volume per unit mass. Since the volume is given and you have already calculated the specific volume, you're going to find out the mass. The mass is going to be substituted here. Specific volume 1 you determined. Specific volume 1 is going to come here. And let's talk about specific volume 2. So for this, you know the temperature and you know the pressure, P2. So these two things you're going to use to find out specific volume 2. And this is something you're going to come here. And that's it. You're going to substitute all the values and you're going to get the answer. Do you understand the blueprint of the solution? First of all, do you understand the problem statement and do you understand the blueprint of the solution?
Yes, sir.
Okay. So now look at the solution itself. So we have work done equals to P V2 minus V1. Okay, V1 we're going to get at the specific pressure, F value, since it is saturated liquid. So it will be 0.00088458 from the table A12. Then we're going to substitute here. The volume was given in liters. So to remember the conversion between liter and meter cube. So 1 meter cube is equals to 1000 liters. Okay, so you have to multiply it with by 0.001 to convert it to meter cube, divide by the specific volume, which you have already determined from the table. So you'll get what is the mass. Then for state point 2, you have the temperature and pressure. First, you go into the saturation table. You will find out that it is in the superheated state. Then you go into the superheated table, and at that specific temperature and pressure, you can find out what is the specific volume, V2. And then corresponding to V2 and V1, you just substitute everything into the main formula, and you get what is the work done. Is the solution of this problem clear? Is there anything within the solution, any step which is not clear? Please feel free to ask. Are you catching up with me? Is it clear? I need an answer. I need yes or no. If
Yes, sir.
no,
Yes, sir.
okay. If no, you let me know that what step is not clear so that I can explain. Anyways, look, student, I would request one thing that during my lecture, as you have seen already, I need an active response. Okay, if it's no problem if there is something you're not able to understand it, if you say even 10 times, if you ask me to repeat it, I will have no problem repeating it. But I need an active response, whether you are actually understanding it or not. Okay, if not, then you have to tell that what is the specific thing that you did not understand. So, because this is a cooperative way, learning cooperative way is much better. okay, rather than I just keep on talking and have no idea whether you are understanding it or not. Okay. Shall I move ahead?
Yes, sir.
Okay. Okay, so let's see this one. We have a piston cylinder device initially contains 0.4 meter cube of air. So this was the initial volume of air at 100 kilopascal and 80 degrees centigrade. So 100 kilopascal is P1, 80 degrees centigrade will be T1. Okay, the air is now compressed to 0.1 meter cube. So we have V2 in such a way that the temperature inside the cylinder remains constant. So it's very clear. Temperature inside the cylinder remains constant means it's an isothermal process because the temperature is constant. Determine the work done during the process. So we have P1, we have T1, we have V1, we have V2. These values are there with us and we know it's a constant temperature process. So the solution will be very clear. We have to use the formula for the work done for the constant temperature process. Okay, so that's the formula here. So we can directly use P1 V1 ln V2 by V1. Okay, and we know V2, we know V1, we know V1, we know P1. We just substitute the values, you'll get the work done. Is the solution clear?
Yes, sir.
Okay, next we have a topic here of specific heats. So let's discuss this topic. Specific heat is basically what it is the energy required to raise the temperature of a unit mass of a substance by 1 degree. Okay, so suppose if I have, let's say I have water here. Okay, so suppose I have water and the water is at 24 degrees centigrade. So suppose if I want to raise the temperature of water from 24 to 25 degrees centigrade, okay, I need to supply some energy, Q. This energy is the specific heat. So specific heat is basically what? It is the energy needed to raise the temperature of water from 24 to 25 degrees centigrade. Okay. So this energy, which is needed to raise the temperature of any substance by 1 degree, is known as a specific heat. Okay. First of all, a specific heat is a material property. Okay. What do we mean by a material property? We mean by material property is that if you change the material, a specific heat will change. So if I want to raise the temperature from 24 to 25 for water, the amount of energy needed will be different if instead of water, let's say I had oxygen. Okay. So suppose I had oxygen and I want to raise the temperature of oxygen from 24 to 25. It will be different amount of energy than whatever the energy was needed for the case of water. Why? Because this specific heat is a material property. It depends upon the material. You change the substance, the specific heat is going to change. Okay, so this is very first thing. The second thing is that it also depends upon temperature. Okay, so the specific heat of a substance changes with temperature. Suppose we are talking about water, so the energy needed to raise the temperature of water from 24 to 25 degree will not be the same as the energy needed to raise the temperature from 25 to 26 degree. Okay. So these two Qs will be different. They will not be same. So it is also a temperature. So specific heat also changes with temperature. So it changes with material. If you change the material, specific heat will change. But suppose even if the material is same, still if you change the temperature, the specific heat value will be different. So the amount of energy needed to raise the temperature of water from 40 to 41 degrees centigrade will not be the same as the amount of heat energy needed to raise the temperature of water from 75 to 76 degree. So if you change the temperature, then the specific heats will change. If you change the material, the specific heat will change. Okay, but anyways, the specific heat is basically what? It is the energy needed to raise the temperature of a unit mass of a substance by 1 degree. Its unit will be kilojoule per kg degree centigrade or kilojoule per kg Kelvin. Okay, so kilojoule is the unit of energy needed to raise unit mass of a substance. So it's kilojoule per kg by 1 degree per degree centigrade or per degree Kelvin. Since it is about the increment of temperature, since we are talking about the increment of temperature delta T, okay, so delta T is same whether it is in degree centigrade or it is in Kelvin, so that's why it doesn't matter, both these units are okay. Kilojoule per kg degree centigrade or kilojoule per kg Kelvin, these both are the units for the specific heat. Because we are talking about increase in temperature by 1 degree. So 1 degree rise means delta T. So delta T for the case of degree centigrade, for the case of centigrade or for the case of Kelvin are both same. So anyways, do you understand the general concept of a specific heat? What is a specific heat?
Yes, sir.
Okay. Okay, now we have another concepts related here. What is, we call it a specific heat. First of all, how do we represent a specific heat? We represent a specific heat by the letter C. Okay, but with the letter C, we write a subscript. The subscript sometimes is written CP and other times it's written CV, and they have a specific meaning. Okay, whenever it's written CP, so CP means specific heat at constant pressure. Means the energy required to raise the temperature of a unit mass of a substance by 1 degree as the pressure is maintained constant. And CV is a specific heat at constant volume. So that is the energy required to raise the temperature of the unit mass of a substance by 1 degree as the volume is maintained constant. Okay, what is the difference between these two things? Let me explain this to you now. Suppose I have a piston cylinder device. Okay, within this piston cylinder device, what I do is that I fix the piston. Okay, so the piston cannot move up and down. Okay, suppose inside I have water. Okay, and what I do is that I heat the water. So once I heat the water, I'm supplying energy. Okay, so let's say Q is being supplied here. So all of the energy supplied will be used to raise the temperature of water. Now suppose 1 degree rise requires 4 joule of energy. So let's say when I have supplied 4 joules of energy, then this 4 joules, all of them will be used to raise the temperature of water. And this becomes my specific heat at constant volume. Why at constant volume? Because I fixed the piston and I'm not allowing the piston to move up and down. Okay, so volume is fixed, and so the energy, let's say 4 joules was needed to raise the temperature by 1 degree. So if I supply 4 joules, then CV is basically the specific heat of energy, which is 4 joules needed to raise the temperature of water by 1 degree. Okay, now let's consider another case. Suppose I have another piston cylinder device. This time I do not fix the piston. This time I do not fix the piston. So piston is able to move up and down. Okay, inside I have water. Okay, and this time again I heat it. Okay, now what's going to happen when I'm going to heat it? Since the piston is able to move up and down, so this means because of the heating of water, water will expand and it will make the piston to move up. Okay. Now this expansion is something you cannot stop if you have not fixed the piston. So if it's a constant pressure process, in the constant pressure process, you do not fix the piston. That means now you cannot stop the expansion of water. So suppose if I supply 4 joules of energy, now not all 4 joules will be used to raise the temperature of water. But what will happen is that, let's say 3 joules will be used to raise the temperature of water, and the remaining 1 joule will be used to do the boundary work. Because when the piston is moving up, that means that your system is doing some work over the surrounding. Because there is something is being lifted, some work is being done. Okay, and where the energy for this work is going to come? The same energy that you are supplying as heat. This is being used to do the work as well. So now the temperature will not rise 1 degree because we have not supplied enough energy. Just 3 joule is not enough to raise the temperature of water by 1 degree. So now let's say if I supply, instead of 4 joule, if I supply 5 joules, now maybe 4 joules will be used for raising the temperature of water, and then 1 joule will be used to do the boundary work. So this 5 joules becomes my specific heat at constant pressure. So specific heat at constant pressure is basically the energy needed to raise the temperature of any substance by 1 degree under constant pressure. But remember, under constant pressure, you cannot stop expansion. Since you cannot stop expansion, so there will always be some boundary work, and the energy needed to raise the temperature by 1 degree will be higher, because you cannot, part of it will be used for the boundary work, and you cannot stop it. Okay. So this is the difference between specific heat at constant volume and specific heat at constant pressure. Both of them are the specific heats, means the energy needed to raise the temperature by 1 degree. But in case of constant volume, boundary work is not possible, so only the energy provided can be used to raise the temperature by 1 degree. However, in case of constant pressure, boundary work is possible and it cannot be ignored. So the energy that you supply will partly be used to raise the temperature and partly will be used to do the boundary work. So more energy will be needed to raise the temperature by 1 degree. Okay, so in case of constant pressure, larger energy is needed. In case of constant volume, less energy is needed. This is the concept of specific heat at constant pressure and specific heat at constant volume. First of all, do you understand the difference between specific heat at constant pressure and specific heat at constant volume? Is there anything you want to understand? Please ask.
No, sir.
It's clear, right? Okay, now let's look at the formula. How do we write the formula? Okay, so we say that the energy needed to raise the temperature by 1 degree. Okay, so Cp is basically Q. Q is the energy needed divided by del T, means per degree rise. Okay, however, if we when we talk about constant pressure, at constant pressure we know that Q is equals to delta H. How do we know this? We did it last time. We showed it last time that for the case of constant volume process, Q will be delta U. For the case of constant pressure process, Q will be delta H. So if it is at constant pressure, Q will be delta H. If it is at constant volume, Q will be delta U. Okay, so when we look at the definition of a specific heat, so specific heat definition says that energy needed to raise the temperature by 1 degree at constant pressure, but Q will be delta H. So it will be delta H by delta T at constant pressure. And similarly, for the case of constant volume, energy needed to raise the temperature by 1 degree, but Q will be delta U in case of constant volume. So Cv will be delta U by delta T at constant volume. Do you understand these two formulas here?
Yes, sir.
Okay. And so if I continue from here onward, let's say it's Cv equals to delta U by delta T, I can write it in this way, du equals to Cv dt, okay? And suppose if I consider the specific heat as constant value, I can take the specific heat out. So if I take the integral on both sides, so then I'm going to get U2 minus U1 will be equals to, suppose if I take a specific heat constant, okay? So if I consider specific heat constant, then specific heat can come out of the integral. So it will be Cv average, and then it will be integral dt will be T2 minus T1. So U2 minus U1 can be written as Cv T2 minus T1. U2 minus U1 can be written as Cv T2 minus T1, and this was what was written here, the part of the formula which we did not cover last time. Okay, so we said that Q is equals to delta U, which is mu2 minus u1, which could also be written as mcv T2 minus T1. Do you understand this part of the formula which we did not cover last time?
Yes, sir.
Then we have for constant pressure process, it will be Q equals to H2 minus H1, which will be mH2 minus H1, or H2 minus H1 can be written as Cp T2 minus T1. How? Because of the definition of specific heat at constant pressure. So definition of a specific heat at constant pressure is basically what? It says that Cp is equals to dH by dt, or from here we can say that dH is equals to Cp dt. Okay, and if we take the integral on both sides, and if we take the specific heat constant, then the specific heat is going to come out of the integral. So it becomes H2 minus H1 Cp T2 minus T1. So H2 minus H1 can be written as Cp T2 minus T1, which is the other part of this formula. For constant pressure process, Q is equals to mCp T2 minus T1. Remember, these formulas we can only use if we are considering specific heats as constants, because when you consider specific heat at constant, then specific heat comes out of the integral, and then we come up with this formula. But if we do not take a specific heat out of the integral, if we do not assume a specific heat is constant, then we cannot use this formula. Okay, then we cannot use these formulas, then we have to return back to these ones. So for constant specific heats, this one can be used with Cp and Cv. But for variable specific heat, we cannot use Cp and Cv, then we have to use this one, mH2 minus H1 or mu2 minus u1 for constant pressure and constant volume process. Okay, let's talk about a special case for ideal gases. Okay, for ideal gases, we know that enthalpy is U plus PV, but for ideal gas, we know that PV equals to RT. Since we know PV equals to RT, so we can replace instead of PV as RT, so it becomes H is equals to U plus RT. If we differentiate it with respect to temperature, so it becomes dH by dt equals to du by dt plus R. If you differentiate RT with respect to temperature, it just becomes R. And then dH by dt is basically the definition of Cp, specific heat at constant pressure, and du by dt is the definition of Cv. It becomes Cp equals to Cv plus R. For constant temperature, it becomes Cp equals to Cv plus R. So we have this formula valid only for the ideal gases. Why? Because we use the ideal gas assumption. By using this assumption, we come up to this formula, and which says that Cp is equals to Cv plus R. So this can only be applied to ideal gases. Okay. Then we have another term here, specific heat ratio. Specific heat ratio is the ratio of a specific heat at constant pressure to a specific heat at constant volume. For ideal gases, Cp will always be greater than Cv. Cp will always be greater than Cv because Cp is equal to Cv plus R. R cannot be 0. So it cannot be 0. Since R cannot be 0, so Cp is always greater than Cv. Since Cp is always greater than Cv, so K will always be Cp upon Cv. That means it should be, K should be greater than 1. Does this make sense to you?
So can you say that again?
Okay. What we are saying is that for the case of ideal gases, Cp will always be greater than Cv. Do you understand this thing? Because the relationship is Cp is equals to Cv plus R. R cannot be 0. So that means Cp is always greater than Cv. Do you understand this thing?
Yes, sir.
If I'm saying Cp is always greater than Cv, then specific heat is defined as Cp upon Cv. So what do you think the value of K will be? It will always be greater than 1. Why? Because in the numerator, you have a bigger value than the denominator. Make sense?
Yes, sir.
So K less than or equal to 1, not possible for case of ideal gases. Okay, this was a point to highlight. Okay, anyways, let's move ahead. Let's see this example. We have air at 300 Kelvin and 200 kilopascal is heated at constant pressure at 600 Kelvin. Determine the change in internal energy of air per unit mass using data from the table or by using the average specific heat value. So what do we have here? We have air at 300 Kelvin. So this is temperature T1. And the pressure is 200 kilopascal, so that's the pressure P1, is heated at constant pressure to 600 Kelvin. So this will be our T2. Okay, so this is T2. Determine the change in internal energy of air per unit mass. So we need to find change in internal energy, delta U. Delta U will be U2 minus U1. We can get this directly from the data from the table. So let's say if we go into the table, or if you go into table A17, so for the case of ideal gas properties of air, we have table A17. If we go into that, here's this table A17. So we have all the values corresponding to the temperature here, because on the leftmost column we have the temperature. So we have 300 Kelvin. So this is 300 Kelvin, corresponding to 300 Kelvin. The U value will be this. Then we have 600 Kelvin, corresponding to 600 Kelvin. We have the U value this. So we have U1 and U2 with us. We're going to use that U1 and U2. To get what is the change in internal energy. This is if we want to use the table. Do you understand this thing?
Yes, sir.
Suppose if we have constant specific heat values, so we are going then we will not like to use the table. Rather, we are going to take the value by using the average specific heat value. Okay, so in this case it will be delta U equals to CV delta T, which will be T2 minus T1. Okay, so T1 is known, T2 is known, CV we are going to find out at average temperature. So average temperature will be what? 300 and 600. So average of 300 and 600 will be like 450. So first you can see the solution here. So the air heated from 300 to 600 Kelvin. You take the values of U1 and U2 from the table, get U2 minus U1, that will be delta U directly from the table. But when we have to solve it using constant specific heat values, so we need CV at the average temperature. So first we need to know what is the average temperature. So average temperature will be 300 plus 600 divided by 2, that will be 450 Kelvin. Now we need CV value for air at 450 Kelvin. So what we can do is that we can go into table A2. So in table A2 we have CV value for air at varying temperatures. So temperature that we are looking forward is 450 Kelvin. So that's a 450 Kelvin. So we're going to use this, and corresponding to that, we're going to get the value of CV. So this will be the value of CV. We'll come back into our solution. So we take the value of CV, then use the value of CV here, and we're going to get the delta U value. If you look here, the delta U value, if you use the constant specific heat, and delta U if you get from the table, they both are almost the same. It's 220.71, 219.9. There is a very little difference in it. However, there are certain conditions when the difference becomes so significant that you cannot really ignore the variation in specific heat. When you're getting the values from the table directly, then you are actually considering the variation in the specific heat values. But when you are using the C average value, that means you're considering specific heat as constant throughout the entire temperature range. So this might be okay for some cases, but for other cases, there might be bigger difference between these two delta U's. So if the differences are bigger, then you have to use the values from the table. But if the difference is less, then you can actually use this approximation. So this approximation is valid only when the specific heat variation with temperature is small, and we can consider specific heat as constant. So anybody have anything to ask regarding the solution of this problem? So far, are you catching up with me?
No, sir, we don't have any questions.
Okay. Okay, then we have, let's talk about for the case of liquids and solids. Okay, you have to understand one thing, that the value difference between Cp and Cv is because of the expansion. So the boundary work done by the expansion. Now for the case of gases, this boundary work is significant. For the case of gases, this boundary work is significant because the gases expands a lot. However, for the case of liquids and solids, this expansion is very, very small. So for example, if you have a solid and you heat it, the solid will expand, but the expansion of solid will be very, very small compared to the gas. And similarly, for the case of liquids, liquids are many times considered incompressible because even when you heat them, their expansion that takes place with over the liquids is very small compared to the one that takes place with the gases. So for the case of incompressible substances, where the expansion is very, very small, then the Cp and Cv value will be almost equal to each other. Okay, Cv will still be a little higher than Cp will still be a little higher than Cv, but they will be almost equal to each other. Why? Because the expansion in itself is very small. So in that case, for the case of solids and liquids, we can just say that Cp is equals to Cv, and we just simply say as C. Okay, so this is only for the case of solids and liquids. But for gases, we cannot say that Cp and Cv are same. For gases, definitely Cp is greater than Cv, because we have a lot of boundary work because the gases expands a lot. So anyways, this was a little about a specific heat for the case of liquids and solids. Okay, so here there is a problem related to it. A 50 kg iron block at 80 degrees centigrade is dropped into an uninsulated tank that contains 0.5 meter cube of liquid water at 25 degrees centigrade. Determine the temperature when the thermal equilibrium is reached. It's a simple problem. The only thing you need to consider is change in the internal energy of the solid as well as then of that of the water. The solution is done here. You can go through the solution yourself. Okay, if you have any problem regarding the solution, you can discuss it with me later. So with this, our chapter number 4 is finished. This is the summary of the formulas of chapter number 4 I have placed. Okay, and this is a very useful summary. You're going to use it, and it's going to be very handy in analyzing the problems. Okay, with this, our chapter number 4 is finished. There are some practice problems here, but the solutions to the practice problems are already provided to you in the Google Classroom. Okay, until this point, your midterm will be there. So your midterm, which will be in the first week of April, if I'm right. Okay, that midterm will cover till chapter number 4. Okay, so today here we are also going to start chapter number 5, but that chapter number 5 will not be included in the midterm. So your midterm will be till chapter number 4. So at this point, I would like to ask if anybody want to ask anything. If anything is not clear to anybody, you please feel free to ask. Let me know. Let me know where you are feeling trouble so that I can help you in that area.
Sir, an off-topic question. In case there is need of your assistance in a previous chapter, so can we you on campus, or should we set up a meeting on Google Meet with you?
Actually, I'm outside Pakistan, so I cannot be on the campus. Okay. However, what you can do is that if you have, first of all, you have my WhatsApp my WhatsApp contact. Okay, you can contact me on WhatsApp anytime you want. Okay, daytime, nighttime, anytime you can communicate with me on WhatsApp. I am very responsive. I will respond to you on that. The second thing is that suppose if you have a group of students who have some problem and you, in the previous chapters, you want to understand something. Okay, you want me to explain it again to you. No problem. Decide a time among yourself, what time is suitable to you. Discuss with me on WhatsApp. I will, if I agree with that time, we will have again a class session, or you can say it's a help session, where I can explain you the things where you feel difficulty. So no issues in it. Okay, it's just you can find whatever time suitable to you and communicate with me, and then we can have a help session in this regard.
Okay, thank you, sir.
Okay. So the most important thing is that please feel very relaxed with me. Don't feel shy. Don't hesitate in asking questions if you have problem. Okay, no problem. Sometimes what happens is that you think, oh, doctor taught this long time back and I forgot it, and if I ask the doctor, he will be angry. No, not like that. No problem. You have issues, you can ask me. Even I have explained it to you before, I will explain you again. But the point is that if you understand it, then you're gonna go up with me in future. Otherwise, there is no point if I just keep on reading the slides without you understanding them. Okay, so don't worry. If you have issues, let me know. We'll fix it. So do you want any help session for the previous lectures? Or you have sometimes what happens is that a student think that, okay, when we are going to start studying, then we will have problem, then we will discuss. It's okay. If you have not yet even started studying and you decide that, okay, once we're going to start study, and so if you have issues, then just let me know, and then we will have a help session related to that. Okay, but if you have not yet started studying, I will once again encourage you and will put emphasis on it that please start working, because it will become really difficult to catch up with me if you are not working at the same pace. Anybody want to say anything, share anything? Regarding the assignments, anybody have any issues? Okay, let's talk about Walid Jamshed. Are you here with us? Walid Jamshed, are you here with us?
Yes, sir.
Okay, Walid beta, there is a student Hayan. Okay, and
He's
he.
probably a senior, sir. Yes.
Okay, so did you talk with him?
No, sir. I believe Abdul Hadi is acquainted with him.
Abdul Hadi is in contact with him. Abdul Hadi, are you in contact with Hayan?
Sir, Hayam or Hayan?
I don't know the exact pronunciation. It's Hayan, I think. Let me check. It is.
I don't recall. I believe he's a senior of our batch, but let me confirm. Uh, is he in our class?
Okay. Right now, I think
Maybe
he's
he's his senior as well.
okay. Right now, he's not in the class. The only thing is that when I put the survey that all the students are okay for the exam time, Hayan said no. So can you kindly talk to him, communicate with him, so that it's bad if one student is not able to attend the exam.
Okay, sir. I'll talk to him and I'll get back to you soon.
Okay, Abdul Hadi, then I will wait your response. Okay, so please, because now both sections, section A and section B, all are agreed except for one student, which is Hayan. Okay, so kindly communicate with him so that if he also agree with that time, so we will have it in the same time for both the sections. Okay, I will wait your response, Abdul Hadi.
Okay, sir.
Okay. Right now, what you can do is that put your attendance in the chat box, write present against your name, so that I will put the attendance with me later on. Let's have a break of 5 minutes, and after that, inshallah, we are going to start chapter number 5. Okay, students, Assalamu alaikum. Can you hear me?
Yes, sir.
Students, can you hear me?
Yes, sir.
Yes, sir.
Yes, sir.
Can you hear me, students?
Yes, sir, we can.
I cannot hear you. Why? Students, are you able to hear me? Okay.
Yes, sir, we can hear you.
Okay, so let's start chapter number 5. Okay, this chapter is basically the application of first law of thermodynamics. This chapter is the application of first law of thermodynamics, but for steady flow, steady state systems. Okay. So previous chapter, chapter number 4, was basically the application of first law of thermodynamics over the closed systems, but now we will have open systems and which are basically steady flow, and steady state. Okay. So let's discuss about the first law of thermodynamics. The first law of thermodynamics says that we have Q minus W plus E mass in minus E mass out is equals to delta U plus delta kinetic energy plus delta potential energy. So this is the first law of thermodynamics. In last chapter, what we said was that since it was closed system, so we said that E mass in minus E mass out will be 0. But that was in the last chapter. In this chapter, we have mass going in and out. So E mass in and E mass out cannot be 0. Okay. However, what we are saying is that in this chapter, the equipments that we are going to study, the devices that we are going to study, are under steady state condition. Steady state. When we say steady state, that means no change with, when we say steady state, that means no change with time. Okay, so when we say steady state, no change with time means initial values are the same as the final values. So initial and final states are the same because there is no change with time. So that means all of these terms, when we say delta U, delta kinetic energy, delta potential energy, all of these are the differences. These are the deltas between initial and final condition. Now, when we are saying that it is a steady state, means no change with time. That means there will be the difference between initial and final condition will be 0. So what we say is that all of these terms will be 0. Why? Because it is a steady state, and so there is no change with time. So these are basically the steady flow, steady state devices. These are the ones which we are going to study in this chapter, and this will be the main. This will be the main formula, or this will be the form of the first law of thermodynamics that we are going to apply in this chapter. Is it clear so far?
Yes, sir.
Is it clear so far?
Yes, sir. Yes, sir.
I think the students are responding but I cannot hear them. I don't know why. Anyways. Anybody have any issue so far?
No, sir.
No, sir.
Okay. Okay, so we are going to analyze the mass and energy. We are going to make the mass and energy analysis over control volumes. And this will be the first law of thermodynamics that we are going to apply over. These are the lesson objectives. Let's come over to the first topic, which is the mass flow rate. Now, since the fluid is going to be going in and out of our devices, so the mass flow rate itself is very important, and the formula for the mass flow rate is represented here. So mass flow rate m dot is equals to rho AV, where rho is the density, A is the flow area, which is normally the cross-sectional area, V is the velocity. The density, area, velocity, rho AV is the mass flow rate. It can also be written as AV upon specific volume, since density and specific volume are reciprocal of each other. It can be written as AV upon mu. The unit for the mass flow rate will be kg per second. Kg per second. Okay, there's a specific relationship between mass flow rate and volume flow rate, the same relationship which is there for the case of mass and volume. So we know that density is mass over volume, or we can write here that mass is equals to density into volume. So in terms of the flow rate, m dot equals to rho v dot. Okay, so but we know that m dot is equals to rho AV. So AV is basically the volume flow rate. So volume flow rate V dot is basically AV, which is the area, flow area multiplied by the velocity. Okay. When we talk about the control systems, so we have a specific control volume. Suppose I have a control volume, and if the flow is steady, there cannot be any amount of fluid stored within the control volume. That means whatever the amount of fluid going in should be equal to the amount of fluid going out. So this is the fundamental law, which is of conservation of mass, that the amount of mass going in must be equal to summation of all the mass going out. Okay, since the flow is steady and there cannot be anything stored within the control volume. So let's apply these things over a problem here. Okay, so let's study it. Steam, so the thing which is flowing is the steam. Steam steadily means under a steady state, enters a turbine. So turbine is a device. We are going to study about the devices later on, but here let's say this is how the turbine is drawn. Okay, so this is the turbine. Okay, there is a shaft in the turbine. So steam enters a turbine through a pipe with 150 millimeter diameter. So let's say this is a turbine and the steam is entering the turbine. Let's say state point 1 is the one where the steam is entering. So what do we know? We know that what is the diameter of the pipe with which the steam is entering the turbine. The inlet steam is at 20 megapascal and 600 degrees centigrade. So we know what is the temperature and we know what is the pressure. We know the pressure, temperature of the steam which is entering the turbine, and we know the diameter of the pipe through which the steam is entering the turbine. With a velocity of 90 meters per second. So we also know the velocity. of the steam entering the turbine. The exit pipe has a diameter of 600 millimeter. So let's say the steam is exiting from the back of the turbine. So this is the point where steam is exiting. So let's say this is jet point 2. At this point, we know what is the diameter of the pipe. And the steam exits at 300 kilopascal and 150 degrees centigrade. So we know what is the temperature and we know what is the pressure at which the steam exits. Determine the mass flow rate of the steam. So we need to know that what is the mass flow rate of the steam, m dot, and the steam exit velocity. And what is the velocity v2? v1 is known, but v2 is not known. So we need to know what is velocity v2. Okay. Before moving over to the solution of the problem, first of all, we need to understand what is the problem statement. We have a device, which is turbine. What is a turbine? We're going to talk about it later. But we have a device, which is turbine. Steam is entering the turbine with a specific velocity, pressure, temperature, and the pipe diameter is also given through which the steam enters the turbine. Then after passing through the turbine, steam exits the turbine, and the diameter of the pipe with which the steam goes out is given, and the temperature and pressure are given. And what is asked is that what is the mass flow rate of the steam and what is the exit velocity? These are the two things which is asked. Before moving towards the solution of the problem, is the problem statement clear or not? Is the problem statement clear? Well, I cannot hear anybody. I don't know, maybe there's a problem in my computer. You can hear me clearly, am I right? Can you write it in the chat box so that I know that you can hear me clearly? Okay. Anyways, I cannot hear anybody. I have no idea why. Okay, please, if you have any issue, just raise your hand or write in the chat box so that I know that you have any issue. Because since I cannot hear you, I don't know. Yeah. Can you guys hear me now?
Yes, sir, we can hear you.
I cannot hear you. Anyways. Can you please go through the last slide again? Okay. Do you mean this one? Okay. So once again, so what we said is that steam enters the turbine. Turbine, what is a turbine? It's a device right now. Okay, don't need to focus on it, that what is this? It's a device. Steam enters the turbine. The pipe diameter is mentioned with which the steam enters the turbine. The pressure and temperature of the inlet steam is given. The velocity of the steam is given. And then after that, it passes through the device and then it exits the turbine, and the pipe diameter is given, and the temperature and pressure at which the steam goes out is given. And what we need to find, what is the mass flow rate of the steam and what is the velocity of the exit. Velocity at the inlet is given, but we need to know what is the velocity at the exit. Is the problem statement clear? Okay. Now let's try to look at the blueprint of the solution. I mean, how would we solve the problem? Let's have a look at it. Look, if we consider this as a control volume, this is our volume which we are studying. Within this volume, there is a single entry and single exit. Single entry and single exit, and since the steam is entering steadily, Since the stream is entering steadily, this means what? That the mass flow rate going in should be the same as mass flow rate going out. Okay, inlet mass flow rate should be the same as exit mass flow rate. Okay, so there is no mass which is stored inside, so total mass flow rate going in must be equals to mass flow rate going out. Okay, so let's talk about the mass flow rate going in. So mass flow rate going in, the formula for it is AV upon specific volume. Now we know the diameter. Since we know the diameter of the inlet pipe, so we know that what is the cross-sectional area. Because if we know the diameter, we can find the cross-sectional area, pi by 4d squared. Now we know the velocity directly. What about the specific volume? Since we know the temperature and pressure, we can use this data to find out what is the specific volume, and then we use this specific volume here. So we have all the things here so that we can find what is the inlet mass flow rate. Once we have the inlet mass flow rate, then we say that the inlet mass flow rate is the same as the exit mass flow rate. Okay, and then the exit mass flow rate will also be equals to AV upon mu. Okay, and for area, we have the exit diameter of the pipe, so we know what is the area. For the specific volume, we know what is the temperature and pressure at the exit, so we're going to use this to find out what is the specific volume. We already know what is the exit mass flow rate, so we'll find out what is the velocity. Do you understand the blueprint of the solution, how we are going to proceed with the solution? So we know mass flow rate is AV upon mu. By diameter, we know area, velocity was given. By pressure and temperature, we will know what is the specific volume. We're going to use this, find M1. M1 will be the same as M2 or M exit. And then we use this M exit to find out what is the velocity at the exit, because it will be AV upon mu, and mu will be by temperature and pressure. And by knowing the diameter, we will know what is the cross-sectional area, so we can find what is the velocity at the exit. Do you understand the blueprint of the solution? Just write in the chat box yes if you say, or no, because I cannot hear you since. So. Okay, let's see the solution here. Okay, since we will need to find out the mass flow rate, so the mass flow rate is inlet is equals to AI VI upon mu I. AI because we know the diameter, we'll get what is the cross-section area. Then after that, since we know the temperature and pressure, so first we go into the saturation table, we find out that the temperature should be in the superheated region. So we go into the superheated table, we find out at that specific temperature and pressure, what is the specific volume. We're going to use this specific volume into the main formula here. And then substituting the values, we're going to get what is the mass flow rate inlet. Then this mass flow rate inlet will be the same as the exit mass flow rate. For the exit mass flow rate, we know what is the exit cross-section area. Then again, using the temperature and pressure, we'll find out what is the exit volume, what is the exit specific volume. We substitute these two values into the main equation, and we're going to get what is the exit velocity. Okay. So this is the solution. If you have anything to ask, you can ask.
No, sir.
Is the solution clear?
Yes, sir.
Okay. Now, since we are talking about open systems, and within this open system, the fluid can go in and out of the devices that we are going to study. So let's talk about what is the energy of the flowing fluid. Okay. So the energy of the flowing fluid is basically what it is. Suppose if I have a fluid which is not flowing, so a stationary fluid. If the fluid is stationary, then the fluid will have internal energy, which is U, plus the fluid might have some related to kinetic energy, and then the fluid might have some potential energy associated. But when the fluid is flowing, so the fluid always flows when there is a pressure difference. So there is a pressure energy associated with it, and that is known as the flow energy. So we will have a flow energy associated here with it. So this flow energy is basically PV. When you add it with internal energy, that becomes the enthalpy. So for a flowing fluid, we will have enthalpy plus kinetic energy plus potential energy. For non-flowing fluid, it will be just internal energy plus kinetic energy plus potential energy. So for any flowing fluid, whether the fluid is going in or out of our control volume, these are the three sets of energies that we will have. Enthalpy plus kinetic energy plus potential energy. This is all written in the specific terms. If we multiply it with the mass flow rate, we're going to get in terms of the watt. Okay, so m dot h plus v square upon 2 plus gc. So this will be the total energy, whether going in or out. Now let's try to put this into the main formula for the first law of thermodynamics. So we'll have Q minus W plus E mass in. Now there could be multiple fluids flowing into the control volume. Okay, so we will have for each flowing fluid, the amount of energy which is entering with it will be m dot I into hi plus vi square upon 2 plus gci. So this is the amount of energy which will be entering by any fluid entering into the control volume. If there are multiple fluids entering the control volume, you're going to put the sign summation. Similarly, E mass out will be m dot E multiplied by the enthalpy plus kinetic energy plus potential energy. So this will be the total energy going in, this will be the total energy going out, equals to 0 for steady state, steady flow devices. So this becomes our fundamental formula for this chapter. Now, suppose if we have a single inlet and single exit, if we have a single inlet and single exit, then the summation term will be cancelled. Then there will be no summation term. Okay, so we can remove the summation term if we have a single inlet and single exit. And then our formula would somehow look like this. I have placed a summary sheet at the end of this this lecture, and this summary sheet is very important because we are going to discuss all the devices, and the devices that we are going to discuss are all mentioned here in the summary sheet, and how do we apply the first law of thermodynamics over them. Okay, so our first law of thermodynamics equation becomes like this. So we'll have Q minus W plus m dot H1 minus H2. Here 1 and 2 are not the initial and the final. 1 and 2 are the inlet and the exits. 1 being the inlet, 2 being the exit. Plus m dot V1 square minus V2 square upon 2 plus m dot GZ1 plus minus Z2. And this thing should be equals to 0 because it is steady flow, steady state devices. Okay, so this is the fundamental equation of the first law of thermodynamics that we are going to apply for over different devices for open systems. Do you understand this equation or not? Is there anything which is not clear within this equation? Please write in the chat box. Okay. Now let's see the devices. Now we are going to study the devices one by one. Now we are going to study the devices one by one, and we are going to study it from the summary sheet here right now first, and then we are going to go into the slides, and one by one we are going to study all the devices. Okay, before studying the device, let's have a break of 5 minutes, and then we are going to continue again. Okay, Assalamualaikum students, can you hear me?
Yes, sir.
Write down in the chat box, yes, if you can hear me. Good. So let's start. Okay, so we are going to study multiple devices, but we are going to go one by one with them, okay? The very first device which we are going to study now is known as nozzle. Now, nozzle is basically what? It is a specific device which has an objective. The objective of nozzle is to increase the velocity and decrease the pressure. Nozzle is basically what? It is a pipe with a decreasing diameter. So it's a pipe with a decreasing diameter. If we look at even more closely, so it looks like this. It's a pipe with a decreasing diameter, where one is the inlet to the nozzle, two is the exit to the nozzle, and fluid is going into the nozzle and fluid is going out of the nozzle. And what is happening is that as the diameter of the pipe is decreasing, so it increases the velocity. When we say that the velocity increases, what does it mean? It means that the kinetic energy of the fluid increases. Now, where this additional kinetic energy comes from? Energy is not created here. It's basically conversion of one form of energy into the other. So basically at the inlet, we had high pressure, low kinetic energy. Then part of the pressure is being converted into kinetic energy. So our pressure goes down and the velocity increases. So the kinetic energy increases. This is what happens inside the nozzle. So inside the nozzle, basically nozzle is what? It is a pipe with a decreasing diameter. And what happens inside? Pressure energy is being converted into kinetic energy. So pressure goes down and the velocity at the exit of nozzle increases. This is what happens inside the nozzle, and this is what nozzle is about. Okay. So far, is it clear? Okay. Now let's apply the first law of thermodynamics over the nozzle. Okay. Now, if you see, this is the first law of thermodynamics. We have different terminology terms of the first law of thermodynamics. Let's study one by one. First, talk about Q. Now, Q is heat going in and out. Now, what I'm saying is that I wrote here plus as well as cross. I write here tick and cross. It means that it depends upon the problem. Suppose if it is said in the question that the nozzle is adiabatic, then there will be no Q. Q will be 0. But if it is said in the question that there is a nozzle and there is heat going into the nozzle, or the heat is being going out of the nozzle, then the Q will be there. So Q could be there, could not be there, depends upon the question. Okay, so this is about Q. Now let's talk about the second term, W. W is the work done. Now the nozzle is a pipe with a fixed boundary. So this pipe has fixed boundaries and the boundary cannot move. Since the boundary cannot move, there cannot be any work done on the nozzle or by the nozzle. So this thing is for sure that the work done by the nozzle will be 0. Okay, then let's come over to the next term. Change in enthalpy from inlet to outlet. Change in enthalpy from inlet to outlet. Yes, the enthalpy change will be there because enthalpy is basically what? Enthalpy is internal energy plus PV. Okay, and what we are saying is that pressure is going to vary. So that's the main objective of the nozzle, that the pressure should drop. Since the pressure drops, that means there will be change in enthalpy. So from H1 to H2, there will be change in enthalpy. So that means this term will be there in the analysis. Let's come over to the next term. So m dot v1 square minus v2 square upon 2. V is the velocity. Now this is what we are saying. In case of the nozzle, the velocity should increase. Since the velocity should increase, that means there will be change in velocity. So if there will be change in velocity, this means this term is also important. So this term will also be there. Let's talk about the last term. The last term is the change in the potential energy. Now, for the case of a nozzle, if the nozzle is horizontal, then from point 1 to point 2, there will be no change in the elevation. But even if the nozzle is vertical, then the point 1 to point 2, the change in the elevation is very, very small because the nozzle is a small device. So in reality, this terminology, the potential effect terms, will not be there for the case of nozzle. So if we summarize it, this is the situation. So for the case of nozzle, when we apply the first law of thermodynamics, Q could be there, could not be there, depending upon the question. W will not be there. Change in enthalpy will be there. Change in the velocities will be there. But the potential energy change, that will not be there. So our first law of thermodynamic equation could be simplified based upon these assumptions. So this was about the nozzle. First of all, do you understand the application of first law of thermodynamic over the nozzle? How a nozzle is drawn schematically? What a nozzle is about? What are the main objectives of the nozzle? Do you understand this device nozzle? If yes, write yes in the comment. If no, you can write no, and we can explain it. I can explain again. Okay, so we are going to, don't worry, we are going to solve problems related to each and every device. Okay, but right now let's first understand all the devices through the summary sheet, so that when we are going to study all the devices, then we're going to refer back to the summary sheet all the time, so that you know that how things are placed here. Okay, so first device that we studied was the nozzle. Now the second device that we are going to study here is known as diffuser. Now diffuser is basically what? Diffuser is actually opposite to nozzle. Okay, so in case of the nozzle, velocity increases. In case of diffuser, velocity decreases. In case of the nozzle, pressure decreases, but in case of the diffuser, pressure increases. So it's perfectly opposite to nozzle. And in case of the nozzle, nozzle is basically what? It is a pipe of decreasing diameter. Diffuser is a pipe of increasing diameter. So this is the inlet one, this is the exit two, and this is a pipe with an increasing diameter. Okay, so diffuser is exactly opposite to nozzle. And like the way all the terminologies were there in the analysis for the case of nozzle, similar terminologies will be there for the case of the diffuser. Like for example, Q, it could be there, could not be there, depends upon the question. Is the diffuser adiabatic, or is there any heat transfer through the diffuser? That will be mentioned in the question. Work, a boundary work will not be there. Like the case of nozzle, the boundaries are fixed, cannot move. Okay, enthalpy change will be there. The velocity change definitely will be there, because nozzle increases the velocity, diffuser decreases the velocity. And again, the last term will not be there, which is the potential effect term. So this will not be there because diffuser is again a very small device, and there will be definitely not much change in the elevation or the potential difference throughout the diffuser. So this term will not be there. So we studied here right now two devices, nozzle and diffuser, and these two devices are exactly opposite to each other. If anybody have anything to ask, you can write in the chat box. Okay. Otherwise, we are going to stop at this point here, since in section A we also covered till this point here. So we're going to stop at this point here with section B, and we're going to continue from here onward in the next class. So anybody have anything to ask, you can ask. Okay. So regarding your assignments, any queries regarding the assignments? Anything you want to ask regarding your quizzes, regarding the midterm exam? I told you in the midterm exam, chapter number 5 will not be included. Your midterm exam will be till chapter number 4. Okay, since I cannot hear any one of you, right now I'm going to finish this. So do mention the syllabus. Okay. For the quiz, chapter 1, 2, and 3. The quiz will be MCQs, short questions, not short questions, in fact, MCQs. You just see the choices, see the right one. If any calculation needs to be done, you do it yourself on paper and just select the right answer. So it will be 10 MCQs from three chapters, chapter 1, 2, and 3, and that's it. So this will be your quiz. It will be on Friday from 10 to 12. Basically, within half an hour, you'll be done with the quiz. Okay. Then you will have your you will have your midterm exam. Midterm exam is the date, and the day will be specified by the university. Okay. And the midterm exam will cover four chapters: chapter number 1, 2, 3, and 4. Okay, so you will have four chapters for covering midterm exam. Okay, your assignment is due today, and that is related to the EES software. Okay, regarding your assignment, I'm not going to ask anything regarding EES software in any of the exam, whether the quiz, midterm, or the final exam. Okay, so assignment material is going to stay till the assignment. Okay, so I'm not going to ask anything about that in any of the other exam. But anyways, the assignment is due today. If you have issues, you can communicate with me on WhatsApp. My WhatsApp number is with you. Okay, or you can communicate with me on the Google Classroom the way you want. Okay. Uh, Anything else? Anybody want to ask? Okay, what I do is that I will stop my meeting here with you right now, and then I will reconnect. I hope that when I reconnect you, then I can hear you. Okay, so if you have any question, you can ask me in that time. Okay, so right now I'm going to stop my meeting here with you, and then I will reconnect you. Okay, so then if anybody wants to ask anything, you can reconnect with me. Say anything. Okay, let me see if I.
So can you hear us?
Yes, now I can hear you. I don't know, some problem occurred before. Okay, so anybody have any question now, please ask. You have
So
anything to ask? Yeah,
I believe that would be all if I'm speaking for the whole class.
okay. So the whole class leader, Walid, do you have anything to ask? Okay, seems no. But anyways, once again, I'm gonna say you okay regarding assignments, regarding your exams, regarding the lecture material, practice problem. I have uploaded a lot of material for you over the Google Classroom. Anything, if you don't understand anything, feel free to communicate with me. Okay. The object is that you should by the end of this course you should be able to have a good understanding of the course material. Okay. So if you have any issues, you can communicate with me. Extend the deadline for the assignment. Okay.
So what is the
You
EES software that you have mentioned in the assignment?
EES software, it's basically engineering equation solver, and the good thing about this software is that it is normally used worldwide for the course of thermodynamics, heat and mass transfer, and fluid mechanics. For all the three courses, it is a software used almost worldwide. Even the textbook that you're using, if you see the textbook, you will have a lot of references to EES. And there are specific exercise problems for the EES as well. This software was developed by a university in America, and it has now been cached up by many of the researchers. Okay, so it's a very simple software. It's basically an equation solver. So you write a number of equations, and it's going to solve the equations for you. But what's the advantage of this software is that suppose if you have about 10 equations that you need to solve. So when you solve it on paper, it will take you some time to solve those 10 equations on paper. And suppose if you want to do the parametric study, that you want to change one of the parameter and you need to solve the question again maybe 100 times, then on paper it's going to take you 1 week. Okay, it's going to take you a lot of time to do that 100 times. But on this software, you're just going to write all the equations, and then you select a specific parameter that you want to vary, and then you can vary that parameter, and it will solve all the equations maybe 100 times in less than a minute. So that's the advantage. Okay, the other good advantage of this software is that it has built-in properties. Okay, so you can go through the software. It has all the properties for the case of steam, refrigerant, and many other substances. Okay, so you can directly put in the command, and it will give you the property. Okay, whether it's enthalpy, entropy, internal energy, pressure, temperature, density, specific volume, whatever the property, all the properties are there inbuilt in it. They don't need to go and refer to any table. The table is inbuilt in there. So most of the time, for those who wants to do analysis and work over it, it becomes really easy for them to go through this software and work, because you don't have to worry about taking values from the tables. You don't have to worry about writing solving the equations again and again. So this software is going to do this all of these things for you. And the software has a very good presentation in the sense you can write the formulas in the way it could be presented in any paper. So basically, many published articles nowadays are using the software. Okay, I publish all of my articles by using this same software. Okay. Unfortunately, in our university Zabas right now, we do not have the license for it, and that's why I have provided you a version which I just got from the internet. Okay, so this version do not need installation. Otherwise, this is an expensive software, and one cannot really buy it on its own. Okay, but I want you to practice on it. Okay, so that you need to have an understanding about the software, and you need to be up to date with what the world is doing. Okay, this is the main idea. Did I answer your question, Abdul Hadi?
Yes, sir. Thank you.
Okay. The other thing is that a student is asking, can we extend the deadline? I have no problem to extend the deadline. If you want, I can extend the deadline for 1 week. The thing is that if it's going to be beneficial. If you're going to do some work on it, it's okay. If you want, I can extend the deadline. So, okay, for extending the deadline, Walid Jamshed, you are the class representative for section B.
Yes, sir.
And what was the name? Tasawwur Mohsen is the class representative of section A. Okay, I want you two to coordinate. Okay, and just send me a WhatsApp message if you two guys decide and the class decide that you want the deadline to be extended. I will extend it. Okay, you want to extend it 2 days, 3 days, even a week, I have no problem. Okay, so just let me know. Okay, sure. I will wait your response, and I will wait the response of the server. Okay, so because you two are the class representative, so I will consider you to be the one. Your what you say, I will consider as the whole class is saying this thing. Okay.
Okay, sir. Inshallah.
Okay, Jerry, is it okay now? Okay, so Jerry, please communicate with your class leader. Okay, I have no problem. The way, if you want me to extend, I will extend it, no issue. But the thing is that if you have issues, you just work on with it. Let me know. Okay. So the main objective is to teach you something, okay? And the students sometimes get afraid that, oh, doctor is going to deduct mark and do this and that. No, my objective is not that, okay? Marks, inshallah, will be easily flowing. Don't worry about that. So, but the only thing is that you should learn. Okay. Okay. Anything else anybody want to ask?
No, sir, that would be all.
Okay, that's it. Inshallah, meet you on Friday. Okay, not next week. On Friday, for your quiz. Okay. Walid Jamshed, can you send me a WhatsApp message so that I have your WhatsApp number so that if I want to communicate with you, I can communicate with you anytime?
Sir, even I don't have your number. I'll ask the server for it.
No, it's you see in the Google Classroom, I have uploaded the course outline.
Oh, okay.
In the course outline, my WhatsApp number is there. Okay.
Sure, I'll send you a message.
Just send me a message so that I can have a direct communication with you whenever needed.
Sure.
And I hope you are in communication with the whole group, right?
Yes, I am.
Okay.
Okay,
Thank
sir.
you.
Okay, Allah Hafiz.
Okay. Allah Hafiz.
Allah Hafiz, sir.
Allah Hafiz.